This is going to be part 4 of the chapter 5 videos, and this video I'll go over some trig integrals that we haven't covered yet that involve natural log. Like when you integrate them, they turn into some form involving a natural log, namely number 3, 4, 5, and 6. We have not covered those 4. We already know integrating sine and cosine. We have learned other trig integrals, but we haven't learned integrating just tangent or cotangent or secant and cosecant. All right, and so if you want to pause the video, you can go ahead and write these down. But these are all in that table that I put on Blackboard that has the list of derivatives and integrals. But before I go into examples involving these trig functions, I'm going to do a hard example that I didn't cover in the previous video. And this hard example has the integral of x squared minus 3x plus 2 over x plus 1. All right, so we were using in the previous video the integrating natural log, where we had 1 over u du turns into the natural log of the absolute value of u plus c. Now for this problem, if I tried letting u be the denominator x plus 1, because it's usually what I've been doing, just letting u to be the denominator, its derivative is just dx. And then this substitution is not going to really help us any, because if I try to substitute, I still have this stuff up top, x squared minus 3x plus 2. And on the bottom is u. And then du. So this doesn't help. I made it more complicated because now it involves 2 variables. This doesn't. That doesn't help us. So then the next thing I might ask is there another type of substitution I could try? And we've been using u substitution. Well, what if I let u be the top part, the numerator? So if I let u be x squared minus 3x plus 2, its derivative du is equal to 2x minus 3, and then dx. That's not really going to help us either, because I don't have anything involving 2x minus 3. Nothing in the integral and deals with this. So, I mean, this is the original integral. I could essentially, I'll let the top part be u, but then I don't have anything for the x plus 1. You could divide both sides by 2x minus 3, so you have, in substituting in for dx, du over 2x minus 3. Still have 2 variables, u and x. So none of the stuff that we've done so far has worked. So how can we do this? So notice for the fraction, we have a numerator has the higher exponent. So the numerator is a polynomial of a higher degree. than the denominator. So we could try dividing the numerator by the denominator. Which is going to involve long division. And anytime you perform the long division, you'll get something of the form Q plus R over D, where Q is the quotient, R is the remainder, and then D is the divisor. In this case, our divisor is x plus 1. So I could try the long division for this. And now you just have to remember how to do the long division. So set up, I put my divisor out there, and then underneath the division, I guess, whatever long division sign that is called, put the x squared minus 3x plus 2. And so this is going way back to maybe algebra 1 or something, but you take the leading term of x squared minus 3x plus 2 and divide it by the leading term of x plus 1. This would be scratch work. So I just take the x squared divided by x. All right, so that gives me x. So I put x above the term that has x, and then I take x and multiply it with x plus 1. That's x squared plus x. All right, then I subtract that from the x squared minus 3x. I subtract all of that. The x squared subtract out, then you have negative 3x. Then got to keep in mind we have this minus sign, so the negative 3x minus x is negative 4x. And then I would drop down the 2. And then I do this process over again. I take the leading term of this result divided by the leading term of x plus 1. I take negative 4x divided by x, which will give you negative 4. Then I take negative 4 and multiply that with x plus 1. All right, so that's negative 4x minus 4. All right, so we did negative 4x divided by x is negative 4. Multiplying negative 4 to x plus 1, they give us negative 4x minus 4. Then I subtract all of that, which really changes the signs. So really that would be plus 4x plus 4, but the 4x's cancel out. Then I have 2x plus 4 because of the double negative. So that's going to give me, what, 6. Now I stop here because now 6 is a lower degree than the x plus 1. Constant has a degree of 0. So this is our remainder. And up here, this x minus 4, that's our quotient. And what we're using in the denominator, the x plus 1, that's our divisor. So using the long division, we got so we did x squared minus 3x plus 2 divided by x plus 1. So that's going to be equal to the quotient. So our result from doing long division is always going to have this format: quotient plus remainder over divisor. Our quotient was x minus 4. Our remainder was 6. And then the divisor was x plus 1. All right, so then when we integrate, that's the same thing as integrating this result, x minus 4 plus 6 over x plus 1. All right, and then this turns into something that we can integrate, that we're familiar with. All right, so again, this problem is a hard one because we don't know any substitution that will give us a direct way of simplifying the integral. And so we tried two substitutions. The first was using ubx plus 1, just because we've been using the denominator to be u. That didn't work. Then I tried to look at, well, what if you use the numerator? That doesn't help. That makes it more complicated. So then we asked, how can we do this? And usually this is what I use as a last resort, is the long division. It takes a good bit of work. And we decided to do the long division because the numerator has degree 2. It's a degree that's more than the denominator. And whenever you do the long division, your result is always going to be of this format: the quotient plus the remainder over the divisor. So we did this long division. The quotient is the x minus 4, the remainder is 6, and our divisor is x plus 1. So I could say that's what it equals to: q plus r over d. And I just put the integral signs. So now you can integrate this. All right, so I have 4 terms here. If I want to be real thorough about it, I can write it as the integral of each term. So the integral of x dx, and then the integral of -4 dx, and then the integral of 6 over x plus 1 dx. And then integrating x, well, we know from integration rules, integrate u to the n du, that becomes 1 over u, or 1 over n plus 1 times u to the n plus 1. All right, so x becomes 1 over 1 plus 1 times, and then x to the 1 plus 1, which is x squared. And I'll write my constant of integration at the end. And integrating -4, well, that's another integration rule, is integrating a constant. K dx becomes kx plus c. So integrating -4 becomes -4x. So constant's -4. All right, the third one, I'll factor out the 6. And now I'm integrating 1 over x plus 1 dx. All right, now that we dealt with in the previous video. If we have 1 over u du, that becomes the natural log of the absolute value of u plus c. In this case, our u is x plus 1. So then du is derivative of x plus 1 is just 1. So it'd be like 1 times dx is dx. All right, so du is dx. So we're going to have 1/2 x squared minus 4x plus 6 times, and then we integrate this. That's like 1 over u du. becomes the natural log of u plus c. That'll be the natural log. In this case, u is x plus 1. That'll be natural log of the absolute value of x plus 1, then plus c. And that whole thing is going to be our answer. All right, so I figured I would do this example just to show an example where you have to use long division, and then after I use the long division, then we can use our integral rules. All right, so that's the hard example. Now for the rest of this video, do examples involving some of these trig function integrals. And the ones I starred are the ones that we haven't done yet. Again, if you look at the integration table, you'll see all of these listed. So I'll be doing these 3 examples. So for the solutions for these, if the integral involves cotangent, well, I'm going to probably use the integral that has cotangent. So this one, which turns into the natural log of the absolute value of sine. All right, so the cotangent u turns into ln sine of u plus c. What our u is going to be whatever you're taking the cotangent of, in this case theta over 3. Which if you want, you could write that as 1/3 theta. So when you take its derivative, du, well, that's just 1/3 d theta, because it's a constant times theta. So the theta turns into 1, so it's 1/3 times 1, which is 1/3. So it'll be 1/3 d theta. Now here I have just d theta, so I gotta get rid of the 1/3. So multiply both sides by 3. So 3 du is equal to d theta. All right, so that's what I plug in for here. And then I have u is theta over 3. So I can make the substitution. So it'll be cotangent, and then of u. And then d theta is 3 du. So now I'd factor out the 3 in front of the integral. And so I have my cotangent of u du, which turns into this, the natural log of sine of u. So this will be equal to 3 times ln of sine of u plus c. Then I just got to back substitute what u was. Well, u was theta over 3. That's sine theta over 3, and then plus c. Okay, so that's going to be the answer. All right, so similar kind of logic is going to be applied to number 2. It's cosecant of 2x. So I'm going to use the integral that involves cosecant. So it's this one, and that turns into negative natural log of cosecant plus cotangent. So u is going to be whatever we're taking the cosecant of, so u is 2x. Taking the derivative of 2x, that gives me 2, because it's 2 times 1. So du is equal to 2, and then I latch on the dx. So I need to multiply both sides by a half. So that way I can substitute 1/2 du in for dx. All right, so that's my 1/2 du. All right, so now I have the integral of cosecant of u, and then 1/2 du. So I just factor out the 1/2, and then I have my cosecant of u. And then that turns into this. So in this case, it's going to be negative 1/2 the natural log of cosecant plus cotangent. And then I just got to remember to back substitute in for u. And u was 2x. So this would be negative 1/2 ln absolute value of cosecant 2x plus cotangent 2x. All right, in our third example, so it looks a little bit more complicated. So I have a cosine and I have a sine involved. So let's see what I can try to do. So number 3. It's cosine of t, and then 1 plus sine of t, and then dt. Well, I know the derivative of sine is cosine. So if I let u be the entire thing in the denominator, I can use the 1 over u du equals the natural log of the absolute value of u plus c, and hopefully the du part will be involving cosine. So I'm going to let u be the denominator. So du, so the 1 goes away, derivative of sine is cosine, so that's cosine of t, and then I got to latch on my dt. So that's what I have. And the integral is cosine t dt, so that's my du. So I have basically du over u. All right, and then that is the same as just 1 over u du. So ln of u plus c, and then I just back substitute, well, what was u? U was 1 plus sine of t. All right, and that's it. Okay, so that is it for this video. I will be making one more video, and the last video will be covering definite integrals involving natural log and exponential. Okay, so that's it for this one.